I want to ask a question, what is molecular polarity? But let's explain these thoughts and talk about this. Take a look at this molecule, H2. H2 is a molecule that contains two atoms of hydrogen bonded covalently to each other. Okay? So this bond here is a covalent bond called intramolecular. Now we have intermolecular and we have intramolecular. So intramolecular are is the bond between atoms in a molecule. You understand? So for every intramolecular bond, like this one you see over here, they are made up of electrons. So let's say, let me just draw the electrons in orange. So there are 2 electrons that make up every bond. Okay? That's 2 electrons that make up every bond. And there is something called electronegativity. Electronegativity is the ability of an atom to drag the electrons to itself, like the love of electrons. Okay, so some atoms, they have a tendency to drag electrons to themselves more than some atoms. Okay, and measure them using numbers. For example, for nitrogen, it has a negativity of something around 3.0. For hydrogen, the negativity is around 2.1. For carbon, around 2.5. So these are the negativities of each of these atoms. You can see now from the values I gave to you, nitrogen is more like negative than hydrogen and more like negative than carbon, which means that nitrogen loves electron most in this list. It loves electron most. Do you understand? So looking at this molecule now, the negativity of this hydrogen here is 2.1, and for this hydrogen here is 2.1, which means that they both love electron equally. The electrons here will be pulled on both sides with equal magnitude, which means that the electrons here will be symmetrical. What do I mean? I mean that the electrons will be at equal distance between each of the atoms, since they have the same electronegativity. I hope that is quite clear. Let's take a look at our molecule. Look at HCl, for example. Again, the bond between hydrogen and chlorine is called a covalent bond, which is an intramolecular bond. And every bond is made up of what? Made up of electrons. So we have electrons here in this bond. I'm looking at a periodic table now. Let me increase this a little bit. Okay, looking at a periodic table, electronegativity increases in this direction. Okay, and as we go from the left to the right, the negativity increases. So for hydrogen and chlorine is found at the far right, somewhere around here. Hydrogen is found here. As negativity increases this way, it means that chlorine is more like negative than hydrogen. So chlorine will remember electrons more than hydrogen. So it will try to drag the electrons to itself. Even like the electrons here, these 2 electrons here in this bond will be dragged towards chlorine. Okay, it will be taken away from hydrogen, not completely away, but it will be dragged away from hydrogen and dragged towards what? Towards chlorine. So this will give chlorine a charge. Since the electrons are negatively charged, to give chlorine a partially negative charge and give hydrogen a partially positive charge. Okay, this symbol is called, this thing here is called a dipole moment. It's called a dipole moment. Okay, and this arrow is shown as the magnitude of the dipole moment. That moment is represented by this symbol mu, and it is equal to the product of charge times distance. So the distance between this charge, let me circle that, between this charge and this charge, we usually use D or R in pens. So I used R in my example. So the distance from here to here is R, and each of the charges have the same magnitude. So you should know that they have the same magnitude of charge. So when you multiply the charge by the distance, what do you get? You get the dipole moment. Okay, you get the dipole moment. Now note something, that if the dipole moment of a molecule is 0, it means that molecule is non-polar. Take a look at the H2 I explained up here. Okay, that moment is what is charge times R. Is there any charge coded here? Is there any partial positive or partial negative like I explained here? There's nothing here, right? which means that the dipole moment here is what? Is 0. Hence, H2 is non-polar. But in this case here, for HCl, we have a partial positive side, a pole, a partial positive pole, and a partial negative pole. So we use the word dipole. Or so when I say dipole, I mean two electric charges of the same magnitude separated a particular distance from each other. So we call this a dipole. Okay. So since there are two poles, negative pole and a positive pole now, we say that HCl we have a dipole moment of something around 1.1. So hence HCl is a polar molecule. So HCl is polar. Okay. Similarly, if you look at hydrogen fluoride, HF, the bond between them is called a covalent bond, an intermolecular bond. And the electron between everybody, electrons are white, electrons are white, the electrons found in this bond. Again, fluorine is found over here. So fluorine is, let me check that. Fluorine is more electronegative than hydrogen, which means that the electrons here will be dragged towards what? Towards fluorine. And what do we call this? What do we call this thing over here? I explained up here. And it's called the magnitude of the dipole moment. So that means that there will be a dipole moment in this molecule. Okay. So the movement of electrons towards the fluorine will give fluorine a partially negative charge and give hydrogen a partially positive charge. Are you getting that? So since we have a dipole here, it means that HF will have a dipole moment of a particular value. So hence HF, hydrogen fluoride, is a polar molecule. Let's look at H2O, water. Let's see water is polar or non-polar. So later, if you draw your time molecule, something like this, that's a bent geometry. And look at the bond here. The bond between oxygen and hydrogen, there are two electrons here. Okay, because of oxygen is more like negative than hydrogen. If you look at the table, we have oxygen over here and we have hydrogen over there. So oxygen is more like negative, something around 3.0. That's the negativity of oxygen, or something around that. So oxygen is more like negative than hydrogen. Maybe from the electrons here will move in this direction, the dipole moment, towards this oxygen. Okay, giving oxygen a partially negative charge and giving hydrogen a partially positive charge. All right. Similarly, the electrons here as well, they are going to move towards oxygen because oxygen is more like negative. It loves them more than hydrogen. Okay, so that will give hydrogen a partially positive charge. So we have the dipole moment here, right? The other dipole moment here. So they are all moving towards oxygen. So there will be a net dipole moment in this direction. There will be a net dipole moment in this direction. By net, I mean total dipole moment. There will be a net dipole moment in this direction. Okay. I can't really tell the value because you have to do some calculations, but it should be something around 1.8 to 1.80. So because this molecule have a dipole moment, we say that water is polar. I hope that's clear. Let's take a look at more examples. Let's look at HCl. Let me start some examples. HCl. Let's look at CO2. Let's look at BeCl2. Now for NH3, you get something like this. Okay, the lone pair of electron. So again, between nitrogen and hydrogen, which is more like negative. Let's come back to our table. This nitrogen over here, hydrogen over here. So nitrogen should be more or less negative with something around, I think 3.5. Yes, 3.5. That's the negativity of nitrogen. So it's more like negative than hydrogen. And the electrons here, how they move? They move towards nitrogen, or towards hydrogen. They'll move in this direction with a dipole moment, right? Towards nitrogen, give nitrogen a partially negative charge and hydrogen a partially positive charge. Do you understand that? Similarly, the electrons here, how they move, they will also move in this direction towards nitrogen, because nitrogen is more like negative than hydrogen, even this hydrogen here a partially positive charge. Similarly, dipole moment here will also move towards nitrogen, in this direction, giving this a partially positive charge. So you can tell already that dipole moment is vector since it is moving in a particular direction. Do you understand? So there will be a dipole moment here, a dipole moment here, a dipole moment here. So you have to look at the geometry of the molecule. Geometry of NH3 is trigonal pyramidal. So there will be a net dipole. There will be a net dipole in this direction. Because if you look at it very well, they're all moving like this now. So all of them like they are all kind of moving in this direction, giving this part a partially negative charge and this part a partially positive charge. So since there's a dipole moment, since ammonia shows a dipole moment, it means that ammonia is a polar molecule. Let's look at CO2. Let's look at CO2. CO2 looks something like this, right? Okay. Now between oxygen and carbon, which is more or less negative, let's look at our periodic table. We have oxygen over here and we have carbon over here. I saw that negativity increases this way. It means that oxygen is more or less negative than carbon. So the bonds here, how they move? They move towards oxygen or towards carbon. They move towards what? Oxygen, to dipole moment, isn't it? Giving oxygen a partially negative charge and carbon a partially positive charge. Do you understand? Similarly, the electrons here, how they move? They also move in this direction since carbon is less and less negative and oxygen is more or less negative. The dipole moment, giving this oxygen here a partially negative charge. So between carbon and oxygen, there will be a dipole moment here, right? There will be a dipole moment in this direction. Let's assume, I don't know the dipole moment, you have to calculate it. Let's say the dipole moment in this direction was let's say it was 2.0, for example. 2.0 dpi, the unit is dpi. So let's say the dipole moment here was 2.0 dpi. Every dipole moment here is the same thing now, since it's the same atom, they have the same magnitude of dipole moment. Do you understand? So if this part is positive in this direction, and since dipole moment is vector, we can take this direction as plus 0. You can take this direction as plus 2.0 dpi and this direction as minus 2.0 dpi. So where we total the net dipole moment, if you add it up, it's just give me what? 0. So since the dipole moment of CO2 is 0, it means that CO2 is non-polar because it does not have a dipole moment. Looking at BeCl2, drawing BeCl2, it's also linear, or something like this. And between chlorine and barium, which is more electronegative, I think we get the idea now that chlorine is more electronegative because it's on the far left. If you look at it, chlorine is over here, fluorine over here, so it's on the far left, so it is more electronegative than barium. Okay, let me think that the electrons here, would they be symmetrical or non-symmetrical? There will be non-symmetrical, but a word called asymmetrical. Asymmetrical, okay? So that, like all this other ones say, that all asymmetrical as well. Okay, so the electrons move in this direction because chlorine is more or less negative than barium. That will give chlorine a partially negative charge and barium a partially what? Positive charge. Similarly, the electrons will also move in this direction, giving this chlorine a partially negative charge and barium, of course, a partially positive charge. So again, barium in this direction, there will be a dipole moment, right? In this direction, and there will be a dipole moment also in this direction, and there will be equal magnitude but different direction. That's different signs. So that's like I did for CO2, because BeCl2 is linear. So what will happen? The dipole moment here, we cancel out the dipole moment here, giving a dipole moment of what? A net dipole moment of 0, which means that BeCl2 is non-polar. Let's take a look at another example. I'm trying out more examples for you and get the idea of what I'm trying to say. If you look at CH4, which is methane, CH4. Okay, let's draw this well. Let's draw this. It should do something like this. Grab the bond angle, something like this. So we have hydrogen, 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 and hydrogen. Okay, so the electrons here, how they move? They come towards carbon or towards hydrogen. Hydrogen has a negativity of around 2.1, and carbon has a negativity around 2.5. So carbon is more negative than hydrogen. So the electrons here will come like this in this direction towards carbon. Okay. Similarly, this will also come in this direction towards carbon. Come in this direction towards carbon, in this direction towards carbon. Now, because of the way the molecules are arranged, if you look at it from a different angle, you realize that the dipole moment from every direction will kind of cancel out. This will cancel out that, this will cancel out this. So to cancel out each other. You understand? So in dipole moment will be what? Will be zero. You understand? So since the moment of CH4 is zero, it means that CH4 is non-polar. CH4 is non-polar. So to give you to recap, what is molecular polarity? Polarity arises when there is difference in electronegativity of atoms in a molecule. The reason why HCl is polar is because of the difference in the electronegativity of these two atoms, creating what we call a dipole moment. Okay, so as I said, just to recap, I said the electrons will move in this direction, okay, giving us a partially negative charge and a partially positive charge. This symbol, let me circle that, this symbol in red, this thing over here, it is called the dipole moment. The dipole moment. Why these things here are called the bond dipole. The bond dipole. And note that the bond dipoles, we have two bond dipoles here, they have the same magnitude and they are separated by a particular distance out from each other. That's how we calculate for the dipole moment. And also, if the dipole moment is zero, we know that the molecule is what? Is non-polar.